Just a moment. Так, я включил запись. Друзья, это означает, что мы начинаем наш вебинар. Я прошу всех, кто, кроме организатора и кроме выступающего Андраша Ковача, выключить микрофоны. Видеокамеры можно не выключать, а микрофоны прошу выключить, потому что по опыту мы знаем, что посторонние звуки сильно мешают. Сегодня, 24 февраля 2021 года, 16 часов 6 минут московского времени. Присутствует 30 человек. Это большое количество. Я знаю, дальше по ходу вебинара подключится еще кто-то. Вот уже 31 подключается. И это по-английски называется full house. Мы называем это этот антракт, или как там, аншлаг, извините. А англичане называют это full house. Аншлаг — это, видимо, немецкое слово. Сегодня у нас доклад Андраша Ковача. Он вообще-то венгер, но он сейчас работает в Андраш...
Хельсинки.
Он сейчас работает в Хельсинки. Вот. Ну и это он выпустил книгу, и эта книга сейчас находится в печати. И вот это большая честь для нас сегодня услышать некоторые фрагменты из этой книги, о которых нам расскажет Андраш. Ну вот на первый взгляд, вот тут я уже об этом написал в своем комментарии к объявлению к семинару, но он... Maria, may I ask you to switch off your microphone? My microphone. Maria, I talk to you. Я тогда сам выключу. Да, ну возвращаюсь вот к введению. Итак, почему сегодняшний доклад важен для нас? Важен для нас, потому что, ну, я это объяснял в своих вот, как в каком-то комментарии к объявлению о семинаре, но еще пару слов скажу. Вот 5 лет назад, всего 5 лет назад я выступал в ИФТАНе по теме вот сверхединичных устройств и высказал предположение, что формула Джоуля-Ленца неверна, или, по крайней мере, в наших условиях она не работает. Это вызвало такой ужас у присутствующих. Я просто его хорошо помню. Как же так? Этого не может быть. А я напомню, что эта формула 180 лет назад была придумана. 280, сейчас, 1840-1940, да, 180 лет назад была придумана Джоулем и через год переоткрыта Ленцем. И опираться только на какие-то вот затвержденные в каких-то стандартных книжках 40, 50, 60 лет назад истины в новой физике, которой мы занимаемся, видимо, не стоит. Это одна из причин, по которым сегодняшний доклад, он очень важен. Кроме того, я бы хотел обратить внимание вот всех, кто строит экспериментаторов, кто строит свои теоретические модели, обратить внимание на, ну, это уровень не самый высший уровень теоретической физики, который мы сегодня послушаем, но все-таки опора на математику довольно сложную и опора на уже известные математические следствия известных теорий, она очень важна. Поэтому, пожалуйста, вот учитесь, как нужно строить новые теории. Ну, у нас такие люди тоже есть, и они присутствуют сегодня на нашем вебинаре, которые тоже строят свои довольно сложные математические теории. Но они чуть попозже, после Андраша, выскажутся. Итак, сегодня Maxwell's Equations and Occam's Razor by Andras Kovacs. Andras, take a floor, your presentation. Switch on demonstration of your screen.
Okay, okay, I start. It says you have to give me the access, right? It says host disabled sharing.
I gave you permission.
Okay, now it
Please
works. Yes.
try please again, once again.
Yes, okay.
Yes, we see your presentation.
Okay, do you see now the full screen?
Full screen. You switch on full screen.
Okay, okay, great. So this is the title of my presentation, Maxwell's equations and Occam's razor. And this presentation is based on the ideas that we have in the second edition of our book. And here you see the authors that collaborated. So Giorgio Vassallo, Paul O'Hara, Antonino Di Tommaso, Francesco Celani, and myself. So maybe you know some of them. What I would like to say in the beginning is that many of the ideas are in the second edition, but today you can only buy the first edition because we are still discussing. Yes?
Andras, just a moment, Andras. I wanted to remind you that I asked you to tell clear and slow.
Oh, okay.
Now you are talking clear, but a little bit slow. It's
okay. Okay, so I slow down.
Oral comprehension in Russian auditorium is very, very bad. Please slow. Thank you.
Okay, thank you for a reminder. So this book, now you can buy first edition, and we discussed with the publisher about second edition. So much of what I present today is in the second edition, and please be patient a few months, and after a few months it will be available. Okay, so this is the content of my presentation. First, I discuss methodology. In the book, we use the mathematics of Clifford algebra, so I will talk a little bit about that. Then we start from fundamentals, discuss about Maxwell's equation and the problem of gauges. And then we will apply this to describe the electron. And we will try to understand better what is electric charge, what is Zitterbewegung. And then we'll make sense of what the electron's charge radius and quantum radius physically mean. We will review what it means that the electron's mass may be electromagnetic field energy, and then we discuss relativistic transformations, and we will apply this theory to calculate the anomalous magnetic moment. Now I will say a few words about charge quantization and the mathematical symmetries of electromagnetism, and after this foundation, we will get to the topic that I think is interesting for many in the audience, to describe neutrino as an electromagnetic wave. That will be the last part of my presentation. Okay, let's start from the methodology. So here you can see the cover of our book. And so the title is Maxwell Dirac Theory and Occam's Razor. So this word Occam's Razor, it is in our title. What it means. Here I wrote down Occam's Razor principle. It means that among different models that fit experimental data, the simplest one must be preferred. So it means that as a physicist, we have to look at the simplest possible way to describe nature and avoid any unnecessary complications. And if we do that, then probably we are doing something correct. And this is a very old principle. It was formulated by Ptolemy almost 2000 years ago. And today it is still a very valuable principle. Many people forgot to use it, but we would like to get back, I think, to using it. The second important principle in our work is that we use consistently electromagnetism and general relativity at all length scales. So what it means that we don't say that Maxwell's equation is only valid here, but not valid here. If you have an equation that you think describes nature, it is describing it everywhere. Whether you look at large distance or short distance, nobody will magically turn off Maxwell's equation. So we believe that it is valid at all the length scales. So I give you a simple example that as we know already in high school, we can calculate electromagnetic energy from taking square of electric field divided by 2. This is electromagnetic energy density. Now, if we take this seriously, it means we cannot work with point charges, because if you would have a mathematical point charge, electric field would go to infinite as you go very close to the point charge. And then it would give you infinite energy density and infinite energy. And this is in physics the renormalization problem. So we don't want to forget infinities. We then right away say that, okay, we cannot work with point charges because that would be infinite energy. So we have to look at some more realistic model of nature. And actually the same goes for general relativity. When we learn at university general relativity, then we usually learn that it applies only at the very big cosmic scales. But this is not what Einstein said. He did not say that general relativity applies only at cosmic scales. The equation of general relativity, they simply say that if you have energy density, then energy density is curving space-time. The more energy density you have, the more space-time curvature you have. And of course, you can apply it to the microscopic world as well. So this is in fact illustrated in our cover, that what you see as a quantum mechanical wave, in fact, in reality, you can also calculate what is the space-time curvature of the electric fields close to the nucleus. And to get a consistent view of electromagnetism and quantum mechanics, we must not forget that general relativity also applies on the microscopic scales, not only on the macroscopic scales. So we want to be very consistent in how we use physical equations. This is our methodology. Okay, now let's start with the mathematics that we will use. So maybe some of you learned Clifford algebra in school, maybe it's new for some of you. For me, I only learned it in the past few years. It was not part of my university education, but it's actually not very complicated. So the basic rule in Clifford algebra is that you have these multiplication rules of basis elements. A basis element is like a unit vector in certain directions. So you can see that if you have a base vector in the x, y, or z direction, then you multiply it by itself, you get 1. If you multiply the time direction by itself, then the square of the time basis vector is -1. And you can also multiply different basis vectors, for example, x and y. And here the rule is that if you multiply basis vector I and j, it's minus the j and I. So switching the order gives a minus sign. And these are the basic rules of Clifford algebra. And you can see why it's useful in physics, because from the first line, you can recognize that this is basically giving you the metric of Minkowski space. This is our space-time metric, so that you can see that Clifford algebra basically captures the geometry of space-time. So it's not a surprise that this will be very useful in physics. So what also you please remember is that when you multiply different direction basis vectors, for example, x and y, then you have this exy that you can think of as an area element. So here, the area elements, we call it bivector. So bivector, just think of as an oriented area element. Similarly, you can think of a trivector. A trivector is a oriented volume element. So you can have multiple dimensions. You can have vectors, b vectors for area, and 3 vectors for volume. Okay, now the rules that we saw in the previous slide, we can apply to multiply 2 space-time vectors. So here I use this notation to write a space-time vector. The first element is the time component with a t index. The second bold is the spatial direction, so it's like a space vector. Okay, so this space vector has x, y, and z components. So now let's look how the product of the 2 vectors is. And if you write p and q, I write here in terms of the space and time components, sorry, the time and space components, and q also, time and space components. And we simply apply the rules in the previous slide to multiply out these different basis components. So again, to go back to previous slide, I only apply these first and second line. These are the only rules I apply. And if you do this multiplication, then this is the result you get for multiplying 2 space-time vectors. You get this first part, which looks like a dot product. So this dot product is the scalar part, and this gives you a scalar. So here, for example, you have the time components multiplied, and here you have the space components multiplied. And this scalar part is a number, and this is symmetric. Symmetric meaning if you exchange p and q, you get the same. And then you have the other part. This is the b vector part. So here you can see that it's similar to a cross product that we learned in the school. So the spatial part is a cross product, and you have a similar construction in the time component. So physicists denote the second part with a wedge product. So when you see the wedge product, you can think of this expression on the top, and this is somehow similar to the cross product that we learned in school, but applied to a space-time vectors. And in terms of dimensionality, this is a b vector, so like an area element, and this is anti-symmetric. Anti-symmetric means that you change p and q, you get a minus sign. Okay, so this is important to remember that in Clifford algebra, if we multiply 2 space-time vectors, we get the symmetric part, which is scalar, and the anti-symmetric part that is written with a wedge product, and this is a b vector. Also, we can define the so-called unit pseudoscalar, and we use the letter I for it. So this is just multiplying the time x, y, and z base products. And the reason why we choose I is because it has some similarity with the imaginary unit in complex numbers. So in complex numbers, if you multiply I by itself, you get -1. And this is also true here, that if you multiply this I by itself, you also get -1. It follows from the rules I wrote in previous slide. But please remember that this is not a complex value. It just has similar properties, but this is in the end a geometric construction that has the dimensions of time and space, and that's why it's called a pseudoscalar, because it behaves like a scalar, but this is not a scalar. So this is a geometric construction. Now, with this definition, we can write also this sigma that's like the gradient in space-time. So when we use in the following slides this bold sigma, then the both sigmas means that we have the space-time gradient plus the change in time, and we multiply that by 1 over c just to normalize the scale of space and time. Okay, so this is our basic overview of the Clifford algebra mathematics. Do you have any question so far about Clifford algebra?
Вопросы у кого-нибудь есть по алгебре Клиффорда?
Okay, then let's go on.
Continue, please.
Okay, let's go on. And now we will apply this to describe Maxwell's equation. So in Maxwell's equation, we learn at university that there is a vector potential field, and this vector potential we use the letter A to denote, and this square index means that this has 4 components. So this is a space-time vector. A is a space-time vector with 4 components, and we apply this space-time gradient sigma that we defined in the previous slide. So we apply it, and we use the Clifford algebra multiplication rules. So we have the first term with a dot product. This is the symmetric term, and then we have the second term with a wedge product. The first term with a dot product, we use S to denote it, and the second term we use the letter F. And F, you will see, is the electric and magnetic, contains electric and magnetic fields. And together we use the symbol G to denote the S and the F, but nevertheless, please remember that they have different dimensions. S has a scalar dimension and F has a B vector dimension, but we can combine the two in this letter G. Okay, so with the Clifford algebra, this Maxwell equation looks quite simple. You just apply the space-time gradient to the vector potential, and you get the electromagnetic fields. Now, the question is, what is the traditional understanding of these symbols? And here, traditional means over the past 100 years. So the traditional view of physicists over the past 100 years has been that we declare S, the scalar part, to be 0, and this has a name. This is called the Lorentz gauge. So when you read Lorentz gauge, it just means that you set S to be 0. And regarding this F construction, which I wrote as E with a gamma t plus IB with a gamma t, I wrote this with a proper multiplication in Clifford algebra, and the standard view of physicists is that we can treat this as a complex number. So you have surely seen this E plus IB expression for the circularly polarized electromagnetic wave. So normally physicists treat it as a complex number, but we want to treat it properly as a geometric construction. Okay, now the question is, why did physicists decide that S can be set to 0? And this was based on the philosophy of how Maxwell's equation was viewed. So first, physicists started with charges, and the idea was that there is some constellation of charges in space, and then from charges they wanted to derive the vector potential field, and there is a formula called the Lienard-Wiechert potential formula that takes the relativistic constraints of the retardation into account and generates vector potential from charges. Then, once physicists had the vector potential, they just wanted to take a space-time derivative to get electromagnetic field. And because they wanted to have electromagnetic field at the output, they did not want any scalar part. The idea was you start from charges, you get vector potential, and from vector potential you get electromagnetic field, and this seemed to fit well with the experiment to just say that scalar part is 0, and then the calculations seemed to match what was measured in terms of the radio wave propagation. So this was the philosophy, but what's wrong with this traditional approach? There are several problems. Firstly, with this traditional approach, charges are external object. You put in by hand because you start with a constellation of charges as your starting point, and you put them in by hand into Maxwell equation. And this way, the physics does not explain what charges are made of. You don't know anything about charges, what they are. So because physicists don't know what charges are made of, they assume that let's make charges a point-like particles. Because if they would be extended, you would have to say, okay, if you have an extended object, you have to say, what is the material, what is the object made of? Because they did not want to answer the question, what are charges made of? They said, let's just make them as abstract points and forget the question of what they are made of. But of course, if you make them abstract points, you have this renormalization problem coming in, because abstract charge point has an infinitely high electromagnetic energy, because all the fields get infinite close to the point. So this is really not a proper procedure. The other problem is that because we put in charges by hand, it remains unclear how charges couple to electromagnetic forces. And the mainstream perspective, I think, is an outdated view, that the view is that if I have two charges, they continuously exchange photons between them, like a ping pong ball game of photons. And the photons are the force carrying particles. So to me, this is somehow a very odd view, that you have these charges and they play a ping pong game, and the force is like a result of a ping pong game. I think we can do more proper field theory than this ping pong theory. And third, and most important for us, the actually applying the Lorentz gauge leads to contradictions, and therefore contradictions tell us it cannot be correct. Here I give a reference of an article. I cannot go through all the details, but in this article, the author gives very clear examples that show that if you apply gauge theory to electromagnetism, then you have physical contradictions, and therefore something is wrong. Okay, so if we have these problems, then let's think how to solve the problem. And because we want to use the simplest way possible, then our proposition is that the simplest possible solution to these problems is to start from vector potential field and take this as a starting point. And use the procedure we had before, and from vector potential field, we use space-time derivative, same as before, and the result should give us both fields and charges. So the only difference with respect to classical approach is that we don't set S to be 0, but we say that actually S has a physical meaning. The scalar field is the corresponding to the charges. So if we set S to 0, it's like erasing charges from Maxwell's equations. But if we just keep S as a real physical object, then we have a field which describes the charges. And in this way, Maxwell's equation can be written very simple way with Clifford algebra. You just say that sigma g is 0, and if you start from g, and if you start from the vector potential, you say that sigma square a is 0. So this is looks very simple and efficient. So we like simple and efficient. So let's try to see if this is actually the proper way to understand Maxwell's equation. Now, most importantly for our discussion, this way of looking at Maxwell's equation it answers the question of what charges are made of. So electric charges are nothing else but a certain type of electromagnetic field. And once you recognize it, then electromagnetism can be formulated as a proper field theory. So we believe that this is the proper starting point to develop electromagnetic field theory, which is really what physicists are after. Okay, now if we
can I interrupt you that
yes.
that moment, and please switch on previous slide. Previous. You never show us during your presentation the scalar part of this expression, charges. Could you, in words now, explain us what consists of this part of this expression? Compare it with well known for us electrical charge and maybe Dirac-Monopole charge. Explain, please, what is consists of this part.
Yes. This will be actually written in the next slide. I will, but here I just say briefly that if you you start from a vector potential. So the vector potential has 4 components. Vector potential is a space-time vector. So A is a space-time vector. You start from that, and you apply this space-time derivative to the vector field. And when you apply the space-time derivative, according to the Clifford algebra rules, you have the first part where you have a dot product, and the second part which you have a wedge product. And in the first part where you have a dot product, because you take a dot product between 2 vectors, you get a scalar, because a dot product takes 2 vectors and gives you a scalar. So this is a scalar field. So it's in every point of space-time, at every point in the space-time, you have a number, a scalar number to this field. And this will be the electric charge. So actually this S will tell you how much electrically charged each point of space-time is. That's what it means. If you have a plus, it's a positive charge. If you have a minus, it's negative charge. Or I should say charge density, because of course we are talking about points in space-time. So what you have with S is actually a number assigned to each point in space-time, and in reality this is a charge density that the space-time has.
And S, it means that S is only electric charge, no magnetic.
Exactly. And if you want, you can also have the magnetic charge, and I will talk about it a little later. But here, to answer your question, you have to have S with a pseudoscalar I. That's magnetic charge in Maxwell's equations. So you remember we had this I in front of the B. So I is the pseudoscalar, and you can also have the formulation where you have the I in front of the S, and so the IS is the equivalent for magnetic charges. And I concentrate first on the electron. So here I wrote only S, but in reality, you are right that there are 2 components here. There is S and there is also IS. And S is the electric density and IS is the magnetic charge density. So that's
Андраш, interrupt, please. I interrupt you. Я хочу объяснить по-русски, может быть, не все поняли. Скорее всего, кто хорошо английский знает, поняли, но, может быть, не совсем поняли. Он сейчас говорит только вот в этой презентации у нас говорит только об электрическом заряде. Вот это поле скалярное поле S это скалар, по сути дела. Отсюда S взялось. Он понимает по-русски, кстати, довольно хорошо. Вот. S. Это есть электрический заряд. Но он объяснил, что у него там в клиффордовской алгебре, значит, есть такая вот хитрая единица четырехмерная, по сути дела, ковариантная такая единица, которую, если приписать вот к скалярному полю, то там внутри будет содержаться и монополе. Но сегодня он рассказывает только об электрических зарядах. Sorry for interruption. Continue, please. Excuse me.
Okay, and F is the electromagnetic fields. So F is the way we understand the electromagnetic field with the electric field, and IB is the magnetic field. Okay, so let's continue. Then your question was, what do we know about S? I only told you that this is the charge density. And if we take the space-time gradient of charge density, then we get the current density as a space-time vector. So what we are doing here, we take S, the scalar field, as the starting point, and we apply the space-time derivative to S. Now, because S is a scalar, when you apply the space-time derivative on a scalar, then it's very simple expression. You can see here, you get a space-time vector, 4-component vector. So this 4-component vector is the J, which is the space-time current density, right? So it tells you that how much charge is flowing, or how much charge is changing along X, Y, Z, or how much it is changing in time. Now, you can also then apply the dot product to the space-time sigma dot product to this J vector. And here what we are doing is that we are taking the space-time gradient of the current flow. So we take the space-time gradient of the current flow, then you see how much current has a gradient in X, Y, Z direction, or how much charges are changing with time. And this space-time gradient has to be 0 because of charge conservation, right? So simply, if you have a region in space-time, then the currents flowing in is the same as the currents flowing out, or otherwise charge is accumulating. So because of charge conservation, this gradient of the current is 0. And then we can combine these two equations. And by combining these two equations, you can see that we get a wave equation for S. See that what the combination of two equations gives is that you have the gradient square of S minus the second derivative of S with respect to time is 0. And this looks like a very ordinary wave equation, but for the scalar field. So we know, of course, from electromagnetism, what is the solution of this wave equation. The solution is that S moves at the speed of light. So what this really tells us, that this scalar field S, it cannot stay in the same place, but the scalar field, just like any of the electric and magnetic fields, must also be moving at the speed of light. So the very same way how fields in the radio wave move at the speed of light, also the scalar field must be moving at the speed of light. Now, at the first sight, this is very strange because, of course, we are used to seeing that electron is staying in the same place. Like, electrons in my body, they don't move at the speed of light, it seems. But how can it be that we think electrons are moving at the speed of light? Well, the solution is the Zitelbewegung that we have here. So in fact, the speed of light movement is not in straight line, but it's in a helix. So what we call Zitelbewegung is the helicoidal speed of light movement of electric charges. And this is the big conclusion that we come to, that every charged object must be moving at the speed of light along a helix path, and what we perceive as the actual movement of the electron is just along the z direction, along the axis of this helix. So this is Zitterbewegung, and this has a very, very long history. So I would say that the history of the Zitterbewegung concept begins with de Broglie. So de Broglie already in 1920s said that to every elementary particle, there is an associated angular frequency where omega de Broglie is mc squared over h bar. This was de Broglie's observational statement, which he just made as a postulate. He could not prove it yet at that time. Then Schrödinger in 1930 said something very similar, and actually Schrödinger came up with the Zitterbewegung as a name, and he said that every particle has a sinusoidal oscillation, which he called Zitterbewegung, and he assigned the frequency of Zitterbewegung to 2 times what the de Broglie frequency was. And he also concluded that the amplitude of the Zitterbewegung is similar to the reduced Compton wavelengths. Very important observations. Now, another German physicist called Höhnl in 1938 decided that actually it's better if the Zitterbewegung is helicoidal, like I showed you in the previous slide, and not as a sinus wave. So he came up with helicoidal Zitterbewegung. Then next step I highlighted here, a paper by Kerson Huang was written or published in 1952. So this is a more detailed study of helicoidal Zitterbewegung, and he successfully derived electron spin from this helicoidal motion. Now, an interesting historical observation, I believe that this study was written by Kerson Huang's teacher, not by him. So in the 1920s and 1930s, these discussions about Zitterbewegung, they were mainstream physics. So this was mainstream physics at that time. However, by 1940, 1950, mainstream physics went into a different direction. And in quantum field theory, they did not like to talk about Zitterbewegung anymore. So in 1952, already quantum field theory was in the fashion. And I think that because it was not a very popular subject, Kerson Huang's teacher, he gave his study to Kerson Huang and said, please publish it under your name. The reason why I think this was the case is because Kerson Huang was 23 years old at that time, in 52, and he never published anything similar after that. After this paper, he went on a very mainstream direction and never talked about Zitterbewegung anymore. And furthermore, this was published in a journal that was read by science teachers. So normally a 23-year-old person doesn't publish in a teacher's journal. So it's very interesting that what happens when something goes out of the mainstream. Then people find these interesting ways to publish their ideas. Okay, so anyhow, back to the history. Next important step, in my view, is that a mathematician called Marcel Ries, he was the first one to apply Clifford algebra to study electromagnetism, and he made very interesting publications where he showed how electromagnetism can be much more logically and simply described with Clifford algebra. Now the most famous physicist, or actually mathematician, David Hastenes, was the one who continued the work of Marcel Ries, and he used Clifford algebra to describe not only electromagnetism, but also helicoidal Zitterbewegung. So I would say that Hastenes continued the work of Marcel Ries, and our co-author, Giorgio Vassallo, in my opinion, has continued the work of David Hastenes. and he actually completed this work, and he properly derived helicoidal Zitterbewegung from Maxwell's equation, and he clarified that the Zitterbewegung frequency is the de Broglie frequency, because ever since the time of Schrödinger, there was always this question mark in the physicist's head: is Zitterbewegung frequency de Broglie frequency or Schrödinger frequency? And I think now we have the correct answer, that the real frequency is the de Broglie frequency. And I will show in the next slide what is the electron model that it leads to. There is one more slide. Before talking about the electron, I want to talk about some subject that we are very familiar with. This is the normal transversal light. So this is, I'm sorry if this is very trivial. This is something that we already learned in high school, how transversal waves propagate and induce each other. There are some points I want to highlight, nevertheless. So first point, as we know and remember from high school, in a normal light wave, electric and magnetic fields induce each other the way it's shown in the picture. Now this mutual induction is described by Maxwell's equation, and very important, the electric and magnetic energy content is equal in a light wave. So, so you cannot ask, is there more electric field or more magnetic field? They are both present the same way, equal energy. Also, what is important in the light field, that there is no charge. So S is 0 in a light wave. So in that sense, the physicists 100 years ago were right when they were only describing light wave, because the Lorentz gauge can be applied as long as you talk only about light wave without any charges. As I showed in the previous slide, if you consider a circularly polarized light wave, you can describe the electromagnetic field by this E plus IB expression, which is almost like a complex number. So we can think of taking its complex conjugate. So what does complex conjugate mean? In this sense, it means that electric field stays the same, magnetic field changes its sign. So F star is E minus IB. So if we multiply these two together, then the number which we get is B square minus E square. So F star is B square minus E square. Now, what is interesting is that from general relativity, you have the Lorentz transformation rules of electromagnetic fields. And if you try to Lorentz transform B square minus E square, you will find that this is Lorentz invariant. So FF star is Lorentz invariant. And that is not a coincidence. In the book, we derive that actually this B square minus E square is the electromagnetic Lagrangian. So you would, of course, expect the Lagrangian to be Lorentz invariant. And this is looks like almost a connection to quantum mechanics, because in quantum mechanics, if we take psi as a probability density, or as psi as a wave function, then how does quantum mechanics describe probability density? Probability density is psi star. So it's very similar how we can describe it in electromagnetism, almost the same way how it's described in quantum mechanics. And this is not a coincidence, because I believe in both cases, this expression gives you the Lagrangian, and the particle, of course, particle trajectory is defined by its Lagrangian density. Okay, so after this refresher from high school, now let's look at the electron model. And this is our electron model that we get by applying Maxwell's equation. So in the electron, very same way how in a light wave, electric and magnetic fields induce each other. Only difference with respect to light is that topology is different. In the electron, you have a charged sphere, and this electric charge moves around in a circle, and this circular movement of the charge is what is going to induce magnetic fields from the middle. And vice versa, the magnetic field that you have here is going to induce back the electric field. Now, because we apply Maxwell's equation on every scale, we can ask us, what is the electric energy density? Now, this is quite simple to calculate because we just sum up the square of the electric field. We have a spherical charge, so we sum up all the electric field down to this radius of the electric charge. So the total electric energy is going to be given by this integral, and when the integral expression has 1 over r squared, when you integrate out the electric field energy, and you do this 1 over r squared from the charge radius to infinity. So what you get in the end is the expression with 1 over r. You integrate 1 over r squared, you get 1 over r from r0 to infinity. So what you have is inverse proportionality between electrons charge radius and electric energy. So if you use the classical electron charge radius, this 2.82 femtometers for R0, not surprising, what you get for electric field energy is 25.5 kilo electron volt. So this tells you that if you use the classical electron charge radius, 2.82 femtometers, then the corresponding electric energy is exactly half of the electron energy. And this gives you the physical meaning of the charge radius. So this 2.82 FM is really the physical size of the electron charge, and you have the scalar field non-zero on the surface of this sphere. Similarly, we can calculate the total magnetic energy. So the magnetic energy is given by this well-known expression. It's 1/2 of phi and I. Phi is the magnetic flux, and I is the electric current. Now, the electric current is very simple to calculate because you have electric charge moving at the speed of light on this circle. So then the corresponding current is E times C divided by the circumference of the circle, 2 pi r. And the magnetic flux is a bit more complicated, but in the book we calculate that the flux is 2 pi h bar over E. It's also quite straightforward calculation. So what you get for the magnetic energy is this expression, h bar c over 2 re, where re is this Zitelbewegung radius. So here we take for the Zitelbewegung radius this 386 femtometers. Does anybody recognize what this number is? Well, this number is actually well known in physics. This is the reduced Compton radius. So if you use reduced Compton radius as the Zitelbewegung radius, then again you find that half of the electron energy is magnetic energy, right? 255 kilo electron volts. So we have the very nice expression, very much analogous to the usual light wave, that half of the electric energy is electric field, half of the electron energy is magnetic field. You have the charge radius given by the classical electron radius, and we have the Zitelbewegung radius given by the reduced Compton radius. And notice that you have in both cases the 1 over r expression. So in both cases the energy is proportional by the inverse of the radius. So we can conclude from this model that electron mass is nothing else but electromagnetic field energy. And this is a very, very important conclusion because it's philosophically important that we finally understand what electron is made of. Electron is made of nothing else, just electromagnetic field, and the energy of the field is the electron mass. So this defines the meaning of Einstein's formula, E equals mc squared. This is exactly what E equals mc squared means. Okay, any question about the electron model?
Вопросы есть у кого-нибудь к этой модели? Вот, Андраш, I have a question. For calculation electric density, you use a space from the infinity till the radius r sub 0.
Yes, exactly.
But what can you say about electrical energy inside of this radius?
It's zero. So there is no electric field inside. So it's just, you can think of it as a ball. The charge is on the surface of the ball. Inside of the ball, there is zero electric field.
It means that you model very coincide with model of Occam, which consider that electron consists of some sphere filled with the electricity and no charge inside of this sphere. Okay, thank you.
Yeah, exactly. Charge is on the surface of the sphere. Yes.
Okay, друзья, еще у кого-нибудь есть какие-нибудь вопросы вот по этой части?
Что такое заряд? What is the charge?
Yeah, the charge is the scalar field. So
what is the scalar field indeed? What is the scalar field? It is mathematical. It is mathematical trick.
No, it's not. No, you will see in the following slides. You will see it's very physical. So let me go back. So the scalar field is derived from vector potential.
And what is vector potential?
So
what is vector potential in reality? Where it comes from?
Yeah, well, that's the question that I think everybody would like to know.
So you don't know, you are basing on what you don't know, and then you're making big steps.
Well, you have to start from somewhere. I mean, what is space?
But not. You can start with that problem. What is vector potential? And
we have to start from somewhere. No, you can ask what is time, and it's very
methodologically. It is methodologically wrong. You have to first describe what is vector potential, where it comes from, and then start.
No. This is exactly the point. This is what I was explaining before, that this was the methodology that they used classically. So since 100 years, this was the methodology that was used.
It was wrong. The methodology was wrong, and you are now right. Why the methodology of 100 years old was wrong? Why?
Yeah, so
Volodya, stop, please.
Here I had a slide about this.
It's discussion. It's not a question.
Okay, thank you.
Okay. Let's go back to this in the question session. But here I had one slide about why the classical methodology, I think, is problematic.
Andras, continue, please.
And well, I want another. You show that the main equation, this one, electric energy density. This electric energy density is estimate. It is not the correct. It comes not from any Maxwell equations.
No, it does. Because this is derived in the book. No.
It is in the book, but it is not right.
You can derive it from Maxwell's equations. That this is the electric energy density. You can derive this from Maxwell equations.
It is not tested. It is not directly tested. And what you are going about, you take the Maxwellian equations, multiply by E, another you take multiplying by B, and then you summarize in them, and then you take this one.
Володь,
from this
Володь,
equation does not go this equation.
Володь,
no.
let us
Okay,
continue.
okay, let us continue.
lecture.
So I just say that what is tested is that electron has
Andras,
511 electrons.
Andras, please, we shall have discussion.
Okay, let's continue from here. So then we had some questions. Of course, it's very important to ask critical questions. And if you tell this model to your friends, I think very often your friends will not believe you right away. Maybe some will believe you, some will not believe you, and it's normal to be skeptical about a new model. So usually, I of course told already to many people or some people about this model, and we get some questions. So I here now will highlight two skeptical questions that I think are interesting questions to consider, because good skeptical questions help you to develop the model. So the first skeptic statement is what about high energy accelerator collisions? So in accelerator, they accelerate electrons to high energy, and then they collide, and then they analyze collision products. And from accelerator, it looks like the electron is very, very tiny, much less than the classical charge radius. So they would say that, accelerator proves that the electron is much smaller. Okay, but we have to remember that when the charge moves at a high speed, the Zitterbewegung radius is actually shrinking down. And this you can see very simple from a geometric model. So the charges move at the speed of light, c, and you have two components to this movement, two orthogonal components. So you have the movement along z direction where the electron moves, and the perpendicular Zitterbewegung. And with the Pythagorean theorem, you square the two, you get c squared. Now, if you have Zitterbewegung movement, of course, the speed is omega times r. So this Zitterbewegung speed is omega squared r squared. And this is a high-speed electron in the left. And then in the rest frame, you have no z speed, you have only omega squared r squared. That is only you have Zitterbewegung speed in the rest frame. In both cases, the speed of the charge is exactly the speed of light. So from this very simple geometric consideration, you can consider that what is the ratio of the Zitterbewegung radius if you have a speed of z. And by solving this equation, you can see that the Zitterbewegung radius shrinks down with a relativistic formula as the electron moves faster. So here is a geographic illustration. You have in the rest frame, you have the maximal Zitterbewegung radius, and the faster the electron moves, the more it is shrinking down. Now, from the previous slide, you will remember that electric energy is the inverse of the radius, right? So inverse of Zitterbewegung radius and inverse of charge radius. So it means that the mass is the inverse of this ratio. And here you get very simply the relativistic mass formula. Relativistic mass is rest frame mass divided by this Lorentz factor. So this is Einstein's relativistic mass formula derived in a simple way. And so we understand that actually when we accelerate the electron in accelerator, of course it looks very tiny because it's relativistically shrinking. And then here comes skeptic comment number 2, who says that, but if you accelerate something, then Lorentz contraction is only shrinking along the z-axis. So you accelerate in z direction, Lorentz contraction is only in z direction. So then our electron would not be spherical anymore, but it would look like ellipsoid or pancake. So this is a naive view, but not correct view, because we must remember that there is also Doppler effect. And Doppler effect applies to all electromagnetic waves. So here I show a simple scenario. Electron moves along the z-axis in a certain speed. And we know from Heisenberg uncertainty that if you have a fixed speed, your position uncertainty is infinite. So if you have a fixed speed of the electron, then it's along the z-axis is like an infinitely spread. So for simplicity, then this moving electron I model as this wave that's going around as a Zitelbewegung. And the wave looks like this because it's the same everywhere, it's spread by Heisenberg uncertainty. So now if you change the your frame by Lorentz transformation, then relativistic Lorentz transformation causes a Doppler effect, and you have to apply the Doppler effect to your wave, to your electromagnetic wave. So what we have is two effects. First, you have along z-axis Lorentz contraction that shrinks by gamma L, and along this x and y-axis of the wave, you have the transversal Doppler effect, and transversal Doppler effect is also shrinking by gamma L, exactly the same way. So what you have is that all three axes, x, y, and z, all three axes, your electromagnetic wave is shrinking by gamma L, by the same Lorentz factor. So it means that electron always remains a spherical charge, no matter how you Lorentz transform it. This is very important to understand, that relativity is very much in line with our model. Okay, so now we jump into deep physics, and we will use what we learned so far to calculate the anomalous magnetic moment. Now, if you talk to quantum field theorists, they will say that, oh, no, be careful, because it's a 50-page calculation to calculate anomalous magnetic moment. Now, what I will show you here is that you don't need 50 pages, you can calculate it in 2 slides. So the magnetic moment is traditionally derived by this mu equals E h bar over 2 times mass of the electron formula. Now notice that in this magnetic moment formula, the only thing that's not constant is the electron mass, right? E and h bar are physical constants. So since we know now that electron mass is derived from electromagnetic induction, any kind of anomalous excess moment means too little deficit of mass, so that it means incomplete induction, right? Now, let me repeat that again. If you have mu anomalously large, it means that mass is anomalously small, which means that your electromagnetic induction is incomplete. Now, let's...
Andras, may I repeat it in Russian?
Yes.
Андраш сейчас говорит о том, что вот эта формула для магнитного момента электрона, она как бы упрощенная, полная, как он ее назвал. Вот. Но это нужно, но известно, что там есть так называемый G-фактор. Вот он там вот внизу, он его сейчас введет. Этот G-фактор, значит, он для электрона один, там для каждой частицы он свой, этот G-фактор. Вот. И он сейчас будет об этом G-факторе говорить, который связан вот с особенностью, вот это геромагнитное соотношение, по-русски, если так сказать. Thank you, Andras. Continue.
Okay, so let's consider how the induction works. So the idea is that the electron makes one circle in this Zitelbewegung circle, and the idea is that you have a complete induction in one circle. I mean, that's what the model is assuming, that it assumes that you have a complete induction of the magnetic field in one circle, and then the process repeats itself. Every circle you have a complete induction of the field. But if you think of the relativistic propagation of signals, in one circle, the electron moves with a speed c, then this speed limit c means that the space volume from which electromagnetic signals propagate is 2 pi times your radius of the circle, right? So electron moves at the speed of light. Also, electric fields propagate at the speed of light. So by the time electron completes this 2 pi r movement, the electric signals can propagate from space from this sphere with the radius 2 pi r. So it means that you don't have the complete electric energy that's participating in this induction, right? We have, in the previous slide, we have derived the formula for total electric energy. So the total electric energy is the integral from R0 to infinity. This is the total electric energy. However, the only electric energy that participates in one turn is the integral from R0 to 2 pi Re, and Re is the Zeta-Bewegung radius. So it means that during one turn, the electric energy that participates in the induction is less than the total energy. And this is exactly the energy that participates. So we can take the ratio. So what is the ratio of total energy and the ratio of the actually participating energy? If you take the ratio of these two expressions, you get this formula, 1 minus charge radius over 2 pi Zeta-Bewegung radius. And the inverse of this ratio is the G factor, the gyromagnetic factor. So what this tells you is that the magnetic induction does not complete in one circle, but it's an iterative process. And in one circle, you have less than the total electric energy participating. The limit is set by the relativistic signal propagation limit. And so the gyromagnetic factor is nothing else than the ratio of the energy that participates in one circle with respect to the total electric energy. So now we understand that there is a mass deficit, and the mass deficit creates this anomalously large magnetic moment. Okay, this is the theory, and very simple. And now we apply this theory to calculate the electrons and the protons' anomalous magnetic moment. So for the electron, we put in the charge radius and the Zeta-Bewegung radius. And the ratio of these two numbers for the electron is actually the fine structure constant. So this is alpha over 2 pi. And because alpha over 2 pi is a small number, that's why this is approximately becomes 1 plus alpha over 2 pi. So this is Schwinger's formula, and this is where Schwinger's formula comes from, but you can see it's only an approximation. And also what is very, very important to remember is that the real control factor is not alpha, because Schwinger thought that alpha is the control factor, but no, the real control factor is these two radius values. Just for the electron, the ratio happens to be alpha. So this is the experimental G factor for the electron, and this is our calculation. So our calculation is 6 digits accurate. It's quite good. Now let's see if we can use the same formula for the proton. Now for the proton, for a long time, the problem was that its radius value was uncertain. And this uncertainty in the real proton radius value was referred to as the so-called proton radius puzzle. So you can read many articles about proton radius puzzle. Fortunately, for last year, there was a breakthrough in this measurement accuracy. And here I highlight this article at the bottom, which was published in Science last year. And this is a new method and a very accurate method for measuring the proton's charge radius. So according to this new method, the proton's charge radius is 0.8482 femtometers. Now, the Zitelbewegung radius we know precisely just from the proton mass. And we substitute these two numbers in our formula. Again, exactly the same formula. And we get 99.99% accuracy of our calculation with respect to the experimental value. So I think that's quite good. And also I want to emphasize that when we published this formula in the first edition of the book, that was already almost 2 years ago. So we published the formula before the actual measurement value of the proton charge radius. So in that sense, it's really a prediction. So we did not fit any numbers. We did a proper prediction because we had the formula before this measurement was made. Okay. So is there any question about the G factor calculation?
Вопросы есть по гермогнитному соотношению? Нет вопросов. Continue, please.
Okay. So two comments that I think this shows that there is some similarity between the electron and the proton. So we see the same physical principle. Whether we talk about electron or proton, we see the same physical principles that are playing out. The other thing that's important, if you think about a muon, the muon has almost the same G factor as the electron. There is only a small difference. So it means that for the muon, if the G factor is the same, then the ratio of the charge radius and the Zitelbewegung radius must be the same as in the electron. So in a way, the muon can be thought of as a scaled down electron, but very similar structure. Okay, let's go on. So now the next point is about the charge quantization. So if you look again at our Maxwell's equation, how we derived electric charges and electromagnetic field from vector potential, we took the space-time gradient of vector potential, and then you have the charges and fields. Now this is a linear equation. So the question comes in, how do you explain charge quantization from a linear equation? Because if you have a linear equation, you have 2 times or 3 times or 4 times the value, it works the same way. It looks like you cannot get charge quantization from a linear equation. And this is correct because we have to remember that it's a linear equation only when you have a flat space-time. And this is where it's important to remember that what I said in the beginning, we apply Maxwell's equation and relativity at all the scales. So what we have to remember is that if you have electric energy density, it creates space-time curvature. So when you get close to the electron, space-time is curved, because that's what relativity tells you. The more electric energy you have, the more space-time curvature you have. And when you take space-time curvature into account, the effective wave equation is no longer linear. And I think that this is also the topic that Dr. Zatelepin talked about in his presentation, and very important realization that the effective equation is maybe no longer linear if you take space-time curvature into account. And we think that this is the basis of the charge quantization. Now, my co-author, Giorgio Vassallo, derives a geometric condition in the book for charge quantization. And what we find is that there are three quantities that are mutually defining each other. You can have E as the electron charge, elementary charge. It's related to the fine structure constant, alpha. So in natural units, fine structure constant is nothing else than e to the minus second power. And it's also related to the magnetic flux of the electron. So if we calculate from our model the magnetic flux, in natural units, the magnetic flux is only 2 pi over e. So we have three quantities that are mutually related. And if you know one of the three, you know all three. So hopefully in the near future, we should be able to calculate at least one of these three, and then we know the other. And this is a very interesting mathematical challenge to see if we can somehow calculate from relativity and Maxwell equation why these numbers take this value. So this is a 100-year-old puzzle, why alpha minus 1 is 137, and I hope we will be able to solve this puzzle in the future. But not yet today. Okay, now the next topic is electromagnetic symmetries. So this is a bit mathematical again. As I mentioned in the previous slide, Lorentz boost preserves E square minus B square. Now the Lorentz boost as a transformation has a SU2 symmetry group. Other transformation you can do is spatial rotation. You can rotate your perspective, and not surprisingly, spatial rotation preserves S square plus E square plus B square. This is electromagnetic energy density. This is not surprising. If I rotate my perspective, of course, the energy density doesn't change. I can look at any direction. Now, spatial rotations also have SU2 symmetry group, and this is a double coverage of the SO3, usual SO3 space-time rotation group. Now, it turns out that there is another transformation which preserves electromagnetic energy density, and that other transformation is if I rotate the time vector in a smart way. I rotate it with the help of this Clifford pseudoscalar. So the Clifford pseudoscalar, remember this I construction, we can exponentiate it. It's a mathematically well-defined operation. And after exponentiating it with some theta factor, this is like a rotation factor. So in effect, I can rotate the time direction between so-called real values and imaginary values. And the imaginary values means the pseudoscalar values. Maybe a better way of saying it, we can rotate the time vector in a way that's multiplying it between a scalar and pseudoscalar multiplication. And this type of rotation also has a U1 symmetry group. So as I mentioned, I is the Clifford pseudoscalar, gamma t is the unit vector in the time axis, and S square plus E square plus B square is the electric energy density. Now, actually, there is somebody who published a similar idea, Mr. Gerrit Kodens. He published this article I here highlight, where he published similar idea, but Mr. Kodens was not using Clifford algebra, and he thought of this as a mathematical curiosity. However, I think this is not just mathematical curiosity, this has a very real physical significance. So now when we consider the complete symmetry group of the energy density preserving transformations, we have the U1 cross SU2 mathematical group. Now we know from Noether's theorem that every symmetry corresponds to a conserved physical quantity. Well, we know what is the conserved quantity with the rotation symmetry. That is angular momentum conservation. In terms of the electron, this is spin conservation. So SU2 corresponds to spin conservation, and U1 part also corresponds to some conservation. And I propose this corresponds to the isospin conservation. Now, in this sense, because we work with electromagnetic quantities, the correct way to say is that this is electromagnetic isospin. Is it the same isospin that physicists are talking about? The history of isospin is also quite old. It was introduced by Heisenberg and Wigner in the 1930s when they were studying the neutron decay process. So they understood that there is something with the neutron that is new to the previous reactions. And they were not quite sure exactly what's happening physically, but they thought that there is some kind of a spin-like quantity that's conserved, but is different than physical spin. So they introduced the term isospin, and in their language, isospin means something which is analogous to the spin, but not physical rotation. Now, today, physicists use isospin in a quite complicated way. The question remains, is my isospin the same as the isospin that was introduced by Heisenberg and Wigner? And I believe the question is yes, but this remains to be validated. So my proposition is that understanding this approach leads to the understanding of neutrinos and isospin, and this we will discuss in the next slides. But before we go to the neutrinos, are there any questions about these last few slides?
Вопросы какие-то есть перед тем, как к следующим слайдам перейти? Ну, вопросы мы задаем с помощью поднятия ладошки тут вот. Поскольку никаких ладошек нет, то можно переходить к следующим.
Okay. So this then is our last topic that we will start to talk about neutrinos.
One moment. 1.5 hour we have webinar. Maybe within 10 minutes, please.
Okay. Okay, I will try. Yes, I think there is only a few slides left.
Okay.
So and this first slide is actually a very trivial slide, and I'm sorry for the trivial slide, but this will be important. So when we detect electromagnetic waves, we have to use the correct equipment for the correct type of waves, right? When we detect gamma rays, we use a scintillator equipment. When we detect radio frequency waves, we use a parabolic antenna to concentrate them. Now, we cannot use gamma, you cannot detect gamma rays with a parabola, and you cannot detect radio frequency waves with a scintillator. I'm sorry for saying the trivial things, but this is important because we have to keep this in mind. And we, of course, today already know that gamma rays are physically the same as radio frequency rays. Only difference is a different wavelengths. Other than different wavelengths, there is no other difference. Yet physically, they appear very different. And the same is true for neutrinos. So if we talk about high frequency neutrinos, there is this fancy scintillator room that we have here in the photos. That's the appropriate equipment. And if we talk about low frequency neutrinos, we have Parkhomov's pioneering experiment where he showed that we can use a parabola to collect low frequency neutrinos, and they induce beta decay rate 1,000 times faster than normal rate. So they have a very real physical nuclear effect. And here is the reference for Alexander Parkhomov's work. Already 15 years ago, this was published. So the reason why this is important to remember is because when I discuss this topic with some people say that, oh, neutrinos cannot be electromagnetic because they use this big scintillator equipment to detect them. But this is, of course, not true. We just have to remember that the difference between high frequency neutrinos and low frequency neutrinos is the same like difference between gamma rays and radio frequency waves. So there is a question. Okay, please ask question.
Анатолий Климов вот хочет задать вопрос. Толь, давай.
Andras, please tell me what the difference between the ordinary electron and protons according to your approach.
Okay. Well, that's a very difficult question because let's go back so that I only talked about the proton here. So here I told you that the proton also has some kind of electromagnetic induction, but there is a big difference between them because from accelerator experiments, it is seen that electron is only one elementary particle. Like electron doesn't fall into two. However, with accelerator experiments, it can be seen that the proton has subparticles inside. So in that sense, the proton is not a real elementary particle because accelerator experiments show that the proton is still composed of several other particles, but regardless of that, the proton has a well-defined charge radius. So what I would say, and this is something that is a little bit speculative because we, let's say, don't have yet, in my view, a very clear data, but it looks like in the electron, you have a charge sphere, and inside the charge sphere, it's empty. There is no electric field inside the charge sphere. For a proton, it looks like you have a charge sphere, but inside the charge sphere, it's not empty for a proton. You still have subparticles inside the charge sphere of the proton. That's my view.
Okay. Most simple question. What's the difference between the electron and positron according to your approach?
Yeah, according to my approach, the only difference is that S is negative for electron and positive for positron. So the sign of the S is the only difference.
What's the difference of the signal charge? It's the nature is not clear according to your charge.
No, the S.
The physics of charge is non-clear and it's only mysteries according to your approach. No difference.
S is a scalar, so S is a scalar, so S can have a positive or negative value. So the difference between the electron and positron is just the sign of the S.
You propose that there is two types of the charges, negative and positive. What's the difference between the positive and negative charge according to your approach?
Well, according to my approach, is just the sign of the S, that S is positive or negative.
Andras, I could advise you to look at the expression from Clifford algebra that S is a multiplication, of two values, two vectors, and it means that in that multiplications, scalar multiplications, two vectors is not coincide but is directed in opposite direction. This is the reason why multiplication could be could have plus and minus sign. It's my advice to you.
Yeah. This is another. This is true that if you look only at the signs, you can have two models which are equivalent. You can say that positrons they have moved forward in time, but their vector potential is opposite than electrons. so that the vector potential signs are different. Or you could also say that electrons and positrons have the same vector potential, but one is moving forward in time, other is moving backward in time. So this is of course true that you have this ambiguity, but I don't believe in moving backward in time, because I think that of course you have the arrow of time defined by entropy. So even if mathematically you could have two approaches, I think because of entropy increase, things have to move forward in time.
Andras, according to your approach, it's not clear what the mass of the positrons, proton, electron.
And what is entropy? And what is entropy in your approach?
Володь, ну да, я задам, потом ты задашь.
Да, потому что это к одному.
Ну вот еще раз, если Андраш понимает по-русски, еще раз по-русски. Значит, вот согласно твоей алгебре, значит, вот есть константы, которые у тебя непонятно откуда берутся. Масса и скорость света. Ты определил так. Но это значит, если ты определил, это значит, ну вот согласно обычной газодинамике, это ты уже определил волны, простые волны Римана, ты уже задал их. Неужели ты это не понимаешь?
Yeah, so the speed of light is cannot be derived. It's a constant. So of course in Maxwell's equations, you can either take c as a constant, or you can have the epsilon, the electromagnetic, permeability to be as a constant. So you either start from saying that nature defines C as a constant, or you can say that the electric and magnetic permeability of space is defined by constant. But these things you cannot calculate. So you have to take some constant as a starting point, because that's in a way that's the relation between space and time metric. So the way I think about it is that
Володя и Анатолий, я считаю, что Андраш ответил на том уровне, которым он сейчас понимает. Вопрос был задан, ответ получен. Андраш, continue, please.
Yeah, okay, let's continue. So we finished with the neutrinos. So about this last question, I summarized that we measure space distance and we measure time distance. And in my view, c is speed of light is a scaling factor that relates how you measure time distance with how you measure space distance. And this is somehow defined by nature, the relation between these axes. Okay, so let's continue.
Можно спросить, а вот диэлектрическая проницаемость откуда берется и чем она определена? И второе, что понимает Андраш под словами энтропия в такой ситуации? Есть ли там энтропия или это просто слова?
So regarding the space and time permeability, you either define C or you define epsilon and mu. So of course you choose. If you define C, you calculate epsilon and mu, or if you define epsilon and mu, you calculate C. But one of them you have to define. The entropy I don't understand well in this context. So to me, the entropy defines whether time goes forward or backward. But of course, I understand entropy only in the sense how we learn it in high school, that entropy is statistically the increase of disorder, but I don't have any more deep understanding of it.
In high school, we are studying that entropy is integral of dq divided by t. And the statistical entropy, which was introduced by Planck, it's some how to say, it's some hypothesis based on works on the Boltzmann.
Yeah, but entropy is a different topic. So I don't have an understanding of entropy. It's a different topic, and I don't have any good understanding of it. But okay, I suggest let's go on with neutrinos, and then after neutrinos we will can come back to the questions. Okay, so now we have some elementary particle reactions that produce neutrinos. One example is muon decay. So when muon decays into an electron, then according to the current physical model, it produces 2 neutrinos. I'm not sure actually if it's 1 or 2, because I don't think it was really measured if it's 2, but that's the physical model. Other reaction, when a neutron decays to a proton plus electron, there is always a third product is called antineutrino, and it's still open question in physics whether antineutrino is same or different than neutrino. But the main point here is that there are certain physical reactions which, when happen, there is always a neutrino being emitted. And actually the energy of the neutrino, the energy density, can be measured. And neutron is a very nice system because it's possible to measure the energy of the proton and electron products. And by measuring their energy, I think here is electron energy, proton energy, and antineutrino energy is the missing energy. So you can have a nice chart of what is the probability of neutrino energy when the neutron decays. You can see that it's a big range. So, so you can see that it spans from high energy to low energy. And of course, the probability here gets small, but nevertheless not 0. So we also have some part of the emitted neutrinos being rather low energy neutrinos. Now, the important point here is that if we see these neutrino emissions always in elementary particle reactions, then the intuition tells us that these must be some trivial solutions of Maxwell equation if they are electromagnetic waves. Because normal light emission is a trivial solution of the transversal wave. And we would not expect an elementary particle reaction to create some kind of a very complex topological solution, but we would expect that a propagating wave must be always some kind of a trivial solution of Maxwell equation. Okay, now another source of neutrinos is from uranium fission. So these are experiments which should have never been done, but unfortunately, well, we know that some uranium fission experiments are being done. And what observation tells us is that 6% of uranium fission energy is carried away by neutrinos. That's quite a large percentage. So far, all the neutrino measurements tell us that neutrinos travel at the speed of light. So when a nuclear explosion happens, what is the speed of light traveling component? It's called EMP, it's called electromagnetic pulse. So this electromagnetic pulse, it cannot be ordinary transversal wave because it has very different effects on materials than normal light waves or gamma waves. So can we identify a neutrino effect with electromagnetic pulse? Now, if we do that, then it tells us that neutrinos should be longitudinal wave. Why? Because what we know from observations is that this electromagnetic pulse, it causes current surges in the material, meaning that it accelerates electrons suddenly to a certain direction. So, so if this is neutrinos, then it means that the effect of low frequency neutrinos is that they accelerate electrons into a certain direction, which indicates that they should be longitudinal wave. Okay, let's summarize so far. If we want to model neutrinos as electromagnetic waves, we are looking for the following properties. We want some trivial solution of Maxwell's equation. And this is something that's a big challenge because you would expect that in the last 100 years, all the trivial solutions were found. We want a wave that travels at the speed of light, a longitudinal wave, and we want it to carry this isospin rotation. Okay, so this is the challenge. And here, my slide is showing what my proposed solution is. So in the book, I describe this kind of trivial solution to Maxwell equation, where if the wave propagates in the z direction, so the electric field points in the z direction with a sinus wave. Magnetic field also points in the z direction, but with a cosine wave. and the scalar field is fluctuating between the real valued and the I multiplied scalar with a cosine and sine factors. So if you put this trivial solution to the Maxwell equation, you will find that, yes, actually, this is a solution of Maxwell equation. So this wave solution is a solution of sigma g equals 0. And you can see right away why was this not found in the last 100 years. It was not found because the scalar field is non-zero, and people were only looking for s equals 0 solutions. So this is the reason why we can identify this new solution. It of course travels at the speed of light because the electromagnetic induction, as we discussed previously, happens at the speed of light. And this is a longitudinal wave. So here I have some picture about the spatial geometry, that the electric and magnetic fields, they always point in the direction of propagation and they fluctuate in their direction. And this is an induction between electric and magnetic field energy. And you can see that it carries isospin so that the E and B fields rotate into each other, and also S rotates into IS. So this fulfills all the requirements that we have for the neutrino solution. And I propose that neutrinos are particles only in the sense that photons are particles, but a more useful way of thinking of neutrinos is that neutrino is an electric wave described by this trivial solution. So here is an example. This is my last slide. How isospin conservation requires neutrino emission. Now first I start with spin conservation example. Think of electron and positron annihilation. When electron and positron meets, we have two circularly polarized photons which are emitted. And why photons? The reason is spin conservation. So these circular polarized photons, they carry away the spin of the incoming particles. Now, similarly, we can now think of the isospin conservation example and specifically think of a muon decay. In the previous slides, we have already discussed that the electron and muon are almost the same particle. They have same structure. You can think of muon as a scaled down electron. It means that muon has the same spin as the electron. So if a muon decays to an electron, there is no change in the spin. So that means that it doesn't have to emit photons. However, we observe physically that muon decay always accompanied by neutrino emissions. So it means that the muon must have non-zero isospin. And I believe that whether a reaction emits neutrinos or not, it tells us whether the isospin of the emitting particle changes or not. This is my proposition. And this is my last slide. So thank you for the attention. And I hope that this new view of Maxwell equation is inspiring for you. So now I see that there is many questions and we can go through them.
Thank you, Андраш. Друзья, ну вот я вижу, тут 4 у нас человека уже выразили желание, наверное, их будет больше, но прошу учитывать, что вот тем, кто задает вопросы, что Андраш, ведь наш товарищ, он рассказывает нам еще не законченную теорию, которую он просит нас поддержать и понять, и, может быть, что-то добавить позитивное из того, что мы знаем. Вот, пожалуйста, при задавании вопросов и при комментарии, пожалуйста, учитывайте. Чижов, пожалуйста.
Андрас, значит, у меня вот такой вопрос. Согласно вашей теории, квант магнитного потока чему равняется? Вы используете тот термин, который уже существует, или вы привносите что-то?
Нет, это интересно, что это другой. So I will say first in English the question. So the question was about the magnetic charge quantum. So here we see So here we see the electric charge quantum, the expression that it's related to the fine structure constant, And by symmetry between electric and magnetic forces, of course, one would expect that the magnetic charge quantum would be something analogous. But it turns out that it's not. And I had a conference presentation in November that you can look back, where I showed physical measurements of the magnetic charge quantum. And the physical measurements show that...
Володь, поясни, пожалуйста, или Валера. Поясни ответ.
Он не закончил свой ответ.
Okay, maybe I will say also in Russian then. So the magnetic charge quantum, for some reason that we don't understand, is very different than electric charge quantum. That's what measurements show, but we don't understand yet why. So I try to say in Russian. So да, мы думали бы, что магнитный...
Андраш, я помогу.
Хорошо, давайте переводить.
Володь, это
да.
Сегодня он говорит только про электрический заряд, а магнитный поток – это некое превходящее. Вот на текущий момент у него это самое квантование. Поэтому он не до конца это понимает. Это правильный вопрос, но сегодня об электрическом заряде.
Да, но я хочу сказать, что о магнитном кванте у меня была презентация в ноябре, когда была конференция прошлого года. Вы помните?
Вот я как раз и задал вопрос. Отличается от тех представлений, которые мы на сегодня...
Да, отличается. Что мы не понимаем, что почему, но магнитный квант очень даже отличается от электрического кванта. И мы не понимаем, что почему это совсем другая цифра. Это интересный вопрос, и не понимаем, почему, потому что было бы логично думать, что какая-то симметрия между электрическими и магнитными силами. Если там симметрия, тогда симметрия, думали бы, что кванты электрического и магнитного тока тоже симметричны, но почему-то эксперимент показывает, что нет такой симметрии.
Так, ответ получен.
Но 2π на Е это...
Спасибо, ответ получен.
Валер, понял, получен. Но 2π на Е это непонятно вообще, что это. H на 2Е, понятно, да. Это из сверхпроводимости, квант магнитного потока.
Ну так он из классической физики эту величину взял. Значит, Владимир Бычков.
Да, я еще хочу сказать, что natural units это система, где h-бар единица и c единица тоже.
И масса. И...
Понятно.
Да.
Я выступлю потом.
Хорошо, Бычков пропускает. Тогда Егоров Евгений задает вопрос.
Так. Ага, слышите меня, да?
Да, слышно. Попробуйте по-английски задать. Да?
Andras, are you calculate Heisenberg non-location for proton and electron?
So can you ask again, calculate what? I don't understand the question.
Excuse me?
I didn't understand your question. Can you repeat?
No, there are Heisenberg non-location for quantum particles.
Yeah, I understand the Heisenberg.
Are you calculate this?
Andras, the question is about Heisenberg relations between position and impulse of electrons, yes. Electricity, energy, and time. The question is about this Heisenberg relations.
Yes. This is something which my co-author is calculating, and this is of course a very interesting question in physics. Where is it coming from, and where does wave-particle duality comes from? Part of the answer is electromagnetic, because there is a vacuum noise in the background. So the background has the vacuum, even if the vacuum is empty, the vacuum is not empty from electromagnetic noise. There is always some electromagnetic noise, and this plays a role in creating Heisenberg uncertainty, but the exact mathematical details they are described by my co-author Paul O'Hara, and I think he has very interesting theory about it that that helps us to better understand the meaning of the Dirac equation.
Окей, я по-русски скажу, значит, все-таки вот Андраш признал, что он сейчас базируется на пустом физическом вакууме, но понимает, что это на самом деле некое приближение, и вот эти вот неопределенность Гейзенберга, она связана, по его мнению, а это совершенно правильное, по моему тоже мнению, положение, что это связано с осцилляциями, по сути дела, с неоднородностями вакуума. Вот. Но сейчас, вот в сегодняшнем докладе этот вопрос не обсуждается, его поэтому тут и нету. Так, ответ получен. И вот Филипп Васикайло, пожалуйста, Филипп Иванович.
Да, я даже не вопрос хотел бы, а как бы рекомендацию, на которую бы...
Филипп, тогда выступление чуть позже.
Да нет, там короткая рекомендация, не использовать отношения Эйнштейна и не называть это, так сказать, преобразованием Эйнштейна. Эйнштейн никогда не преобразовывал массу. Вот пусть он найдет преобразование Эйнштейна, масса корень квадратный, там из единица минус v квадрат, c квадрат.
Хорошо, спасибо за рекомендацию.
Это Андраш, Филипп, это у него есть целая статья у Филиппа Васикайла на эту тему. Там несколько масс преобразования, несколько выражений для преобразования массы обнаружил Филипп Иванович Васикайло. Он об этом подробно пишет. Эйнштейн преобразовал пространство, а массу это потом приписали различные...
Нет, я просто хотел сказать, что надо обратить внимание, что Эйнштейн не делал такого преобразования массы. Он использовал преобразование Лоренца, а Лоренц не массу преобразует, а скорости. И импульс преобразуется, а масса не преобразуется. Хотя в некоторых книжках пишут вот эту формулу. Это ошибка.
Это хорошее замечание, спасибо. Спасибо. И я думаю, Андраш это учтет. Ну, в России хорошая школа, мы это видим, так? Так, следующий...
Ну, вообще УФМ 2-3 года назад и Окунь писал об этом более подробно. Пусть он там ознакомится с УФМ.
Я думал, что это ты, я читал эту статью, это Окунь писал, верно. Так, Филипп сделал свое замечание, классное. Так, вот Николай Александрович Магнитский задает. Один из специалистов по теории поля, вот, аналогичный.
Можно, да? I have some questions.
Okay.
First, what is a neutron in your model?
Oh, the neutron.
Neutron.
Yes. Yes. Well, in this presentation, I do not deal with the neutron, but in the other parts of the book, I actually investigate this question, and I believe that the neutron is an electron-proton composite, so that there is an electron which is very tightly bound to the proton, and that is the neutron, and this can be seen.
Can you receive a magnetic moment of neutron?
Yes, so that I actually do some calculations about it, and the calculations show that when the electrons depart from the neutrons, so I use a similar approach like is described here, applied to the neutron, and the calculations show that if you take the difference between proton and electron, then the difference is h bar over 2.
But structure of neutron must be different.
Yes. So I describe this in the book, and I do this type of calculation, and what the calculation shows is that the difference that the neutrino carries away is exactly h bar over 2 angular momentum. So that the angular momentum of the neutrino that is emitted is exactly h bar over 2.
Thank you. Second question. Is an electron rotating about nucleus in your model?
You mean a hydrogen electron or which electron?
No, in a nuclear, electron is rotating about the nucleus.
Ah, you mean in the neutron?
Around.
The size of your electron.
Andras, the question is about atoms, normal atoms, hydrogen, for example.
Hydrogen. Okay.
Inside atom.
Yeah. Okay. So this is in the. Yeah, this is another very interesting question. That if we go back to the very first slide here, so that
the radius of your electron is significantly more than the radius of proton. It's right, I think, but is electron rotating?
Yeah. So if you take a hydrogen, if you take, for example, a hydrogen in the ground state, the ground state is 1s orbital. So is the electron rotating in the ground state 1s orbital or not? And this is a very interesting question because in our description, yes, the electron is rotating in the 1s orbital around the proton.
The question is has an electron orbit or orbital? Or,
yes.
Or there are no orbit and orbitally in atom.
Yeah, there of course there are these orbits, 1s, 2s, 1p, so forth. So that Dirac, the Dirac solution gives the eigen states, and the Dirac eigenstates are the electron orbitals. So of course the Dirac equation is used the way it's normally used. The question is about the interpretation, because this is a very interesting question. That if you look at the ground state orbital 1s, is spherically symmetric. So that physicists think that because it's spherically symmetric, it's the same everywhere. They think that 1s orbital is a radial oscillation. But if we say that, okay, it's not a radial oscillation, then how can it be spherically symmetric and still have an orbital oscillation? And I was thinking about this question, and my proposition is that one has to realize that in the end, the electron is orbiting not the nucleus, but the center of mass. So that the electron and the nucleus, they both orbit around the center of mass. And the question is, how are these two orbits coupled to give a spherically symmetric electron orbital? And we describe the mathematics of this in the book, that how can you have a spherically symmetric electron orbital and still an angular momentum? And I think the answer is related to realizing that both nucleus and electron rotate around the common center of mass, and you have to look statistically how these two rotations are coupled.
And the last question. You have many formulae, but there is no physical sense and in your model.
Okay.
What is the sense of electron, of proton, of neutron, of vector potential, and many others?
Well, the vector potential is the physical sense.
Yeah, you have no environment continuous medium in your model. You have a vacuum, but there is no physical essence for your your quantities and your.
I think that this is a little bit philosophical question, because your question is, can we define a vector potential field in vacuum? Yes. Or does there have to be something in the vacuum?
From what is vector potential?
Yeah, but this is, I think to me it's a philosophical question, because what you're asking, that can we say that in a vacuum we define a vector potential field? Or does there have to be some material in the vacuum or some entity in the vacuum which creates this vector potential field? But to me it's philosophy, because you can either say that you define a vector potential field in the vacuum, or you can say that there is some material which we don't yet understand, and this material we don't yet understand, it creates the vector potential. To me, this is a bit philosophy, because the main point is that physical reality that we can experiment and measure and calculate is the vector potential. To me, that's the physical part.
Андраш, ответ получен. Вот Николай, он уже отвечал на этот вопрос. У него в его модели векторный потенциал просто спущен Богом на наше пространство.
Но этот вопрос не только к векторному потенциалу, это вообще все. И поля электромагнитные.
Он так его понимает. Давай сейчас дискуссию. Вот он так ответил на твой вопрос.
Да, хорошо.
Анатолий Климов задает вопрос.
Андраш, вот concerning this slide, and everybody knows that there are two radius of electron radius. The first is the classical 2.82 femtometers.
Yes.
And another called Compton radius electron is 386 and .16 femtometers. My question for you, was the electrical energy in the Compton radius? Not the classical radius, but Compton radius. Electrical power, electrical energy.
Well, the relationship between two is alpha, the fine structure constant. So because if you want to integrate only until Compton radius, then your answer will be alpha times less than this.
Yes. It's so we have about 3.73 kilo electron volts.
Yes, exactly.
And namely in this radius, according to my opinion and knowledge of the energy of magnetic fields and electrical fields is equal. It's well-known results.
Yeah. Well, I think this is related. I think your theory is related to this theory. It's very much related.
But according to your estimation, magnetic energy in the Compton radius is 255 K.
No. This is the total. Sorry, this is the total magnetic energy, and the Compton radius defines this oscillation, the circulation radius of the charge, but the calculation is the total magnetic energy. And I think you are right that if you look at a restricted part of space, you again find the two being equal but smaller because you look only at part of the space, not the total. So in both cases, this is total electric energy and this is total magnetic energy.
Phi, what means phi?
It's a flux, magnetic flux.
Magnetic flux, and E?
It is the charge.
Current.
So not charge, current, electric current.
Current. Андраш, may I help you? Толь, вот смотри, как он считает. Вот в его модели он...
Ну, я понял, что он понимает...
Электрон, послушай меня. В его модели электрон создает два тока. Один ток по орбите, а второй ток собственный. Вот когда он эти оба тока просуммирует, у него получается вот этот флакс, который он пишет, поток, и поэтому получается это выражение. Вот если ты два этих движения сложишь, и это правильные, в принципе, действия, вот. Ну, классические, они не квантовые.
Да нет, но все так и делают. Значит, по определению магнитного поля это И умножено на площадь этого витка. Если ты сделаешь, то магнитное поле будет...
Он отсюда и нашел.
На Комптоне точности будет равно электрическому.
Да, и он это применил. Ответ получен.
Нет, а у него получилось на самом деле, что вот он МЦ квадрат разбил на 2. Вот половина из них, видишь, в электрическом поле сидит, а половина сидит в магнитном. И тогда...
Толя, это обсуждение. Это его модель, это обсуждение. Ты вопрос задал.
И тогда масса электрона, она, по сути дела, электромагнитная, понимаешь? А что держит ее?
Ну, это очень хороший вопрос, что держит массу, и я думаю, что это тот же самый вопрос, как квантовая магнитного электрического заряда. Why? So it's the same question like electric charge quantum, and I think that to answer this question, you need to use a relativistic calculation with a curved space, and we have some ideas in the book about this. So if you look at the book, we have some ideas that that relate to the electron stability to answer why is it stable.
Andras, according to my opinion, your approach is not total. It is not
Consistent.
Consistent. Yes, well, thank you very much.
Totally is not totally consistent.
Okay.
Yes.
So I would say that our approach in that sense is consistent. That we use Maxwell's equations consistently.
No, you don't know where Maxwell's equations are taken from.
Well, that's the other question that you were asking whether in reality there is a scalar field or not. So of course we start with this assumption that the scalar field describes charges. So with this starting point, from this starting point we used it consistently. But that's a matter of discussion whether this is the correct starting point or not a correct starting point. And in terms of total, I would like again to emphasize that I would say that the next step is to be able to calculate alpha or E or magnetic flux. So if we can calculate why alpha is 137, of course that will complete the theory. And that's an interesting next challenge and probably a Nobel Prize challenge to calculate this.
Окей, Чепелев задает вопрос. Володь, включи микрофон. У тебя микрофон не включен. Володь Чепелев. Включи микрофон.
Excuse me. I have a question about one paper. May I show my screen?
Yeah, yes, please. Stop.
1 minute. This paper. Do you familiar with this paper?
No, I never heard of it.
Jones by John Wheeler. It is a rather old paper. You see. 1954.
And very old.
Okay.
Very old paper. Very old.
You may see, maybe it is an interesting electron model. You may find something like this. Some torus particles in this model are described like a standing wave in a tor, something like this. Maybe it is interesting for you.
Yes, thank you for the suggestion. Yeah, it will be interesting to look at it because, of course, the topology is quite similar.
Okay, thank you.
Окей, Савченко задает вопрос.
Андраш, could you precise the issue between high frequency neutrinos and low frequency neutrinos? If I clearly understood, high frequency neutrinos has higher energy and hence higher mass, and low frequency neutrinos low energy and lower mass.
No, I would not say about the mass.
And if we move to the next slide, where you show beta decay, you see the difference of kinetic energy that proposed by neutrinos. This is
Let me go there. So yeah. So here you can see the neutrino energy.
Yes,
but I
yes,
would.
it's well known. Yes, it's a well-known graphic. But if the mass of neutrinos is different, low frequency and high frequency, and the velocity is the same, does it mean that in this decay participated all kinds of neutrinos?
No, well, I would firstly, I would not talk about neutrino mass, only about energy, because I see neutrinos very much as analogs to photons. And we don't talk about photon mass, even we just talk about photon energy. And I think this is very much.
We talk about photon mass, and photon mass, you know, have the moment.
Yeah, we talk about energy and momentum. So I think that this is the same here, that we should talk about energy and momentum of neutrinos, but not about the mass. This is my opinion.
Окей, ответ получен. Не о массе, не о массах говорит, об энергиях. И это правильно, это релятивистский подход. Так, Чепелев задавал, Савченко задавал, Панчелюга задает вопрос.
Андраш, in your approach, some electrodynamical systems can serve like a neutrino generator. It's correct?
Yes, I think that this is correct. So that once you understand this equation, you can think, you know, how to generate this kind of waves.
Okay. The second question: can you specify such electrodynamical system? Have you some ideas?
No, unfortunately not yet. So this is the beginning of this work, and I think that probably Alexander Parkhomov has more ideas because he has written a book on this topic. So he probably has more ideas on this.
Нет, ну это обычная система волноводов.
Там генерация сразу и нейтрино, и антинейтрино, потому что лептонное число нужно сохранять. Ответ получен на два вопроса. Бычков задает вопрос.
I want to ask you, if you use the equation for energy, electric energy, you use it only not energy, you use E epsilon E squared divided by 2. And where you forget B mu B squared divided by 2, and where do you hide the pointing vector in this case? So if you consider the derivation of this equation, you can obtain it from Maxwellian equations, where you will have this energy plus integrated over the volume, magnetic energy integrated over the volume, and it will be equal to the flow of pointing vector. Where did you, why you can separate B, E, and pointing vector?
Yeah, they are not separated. They are inducing each other. So this expression that I have on the bottom, this one
you cannot do it. You cannot do it. You cannot do it because you use this equation for energy. So you have to use here the addition of magnetic field. So you cannot exclude it.
If you calculate 1/2 b squared, you get the same result. If you calculate b squared over 2, is the same result as this formula.
But you cannot separate here. You can consider on the side only the sum.
Look, in fact, if we have
stop. You cannot separate them from the Maxwellian equations. You cannot separate them. It is some sort of approximation. If you have magnetic field, then you have to use the sum of it. That is. So I obtained answer.
Стационарный случай, Володь, стационар.
No, не надо.
Yes. I think that this is the correct. That this is the stationary solution, and we have in fact we have two types of derivation.
And then stationary.
My claim is that in the b squared over 2 in the stationary case is the same.
The stationary case is the same. You cannot separate. Please look how it is derived.
У него, можно я скажу, у него очень интересная, но она такая понятная система, при которой электрическое и магнитное поле перпендикулярны друг другу. Поэтому то, о чем ты думаешь, что они должны как-то друг на друга влиять, они при скалярном произведении просто не перемножаются, потому что произведение скалярное равно нулю в этом случае, и поэтому остаются раздельные. Поэтому он разделяет электрическую энергию и магнитную разделяет.
Так они неправильно говоришь.
Ну,
У тебя эпсилон Е квадрат плюс мю H квадрат. Их разделять нельзя.
Valery is right, and you have to remember that this moves at the speed of light. So this is not any speed. This moves at the speed of light, and because of this light speed movement, you have these separate expressions. So Valery
Я хочу сказать следующее, что из формул, которые получаются из уравнений Максвелла, нельзя говорить о том, что одно перпендикулярно, другое параллельно. Потому что у вас эпсилон Е в квадрате, и мю Е в квадрате, и мю H в квадрате, и здесь разделять ничего нельзя.
Look, if you want to have a different approach, we actually derive this electron energy with two different approaches. This is the first approach that's more easy to understand, but we also derive it with a different approach with the Lagrangian current. And with a different approach, we calculate from the Lagrangian current density what is the energy density. And if you take the Lagrangian approach, you also get the same.
Don't frighten me with Lagrangian approach. Please sit on the classical position and please explain me how you can the classical.
The two are equivalent because you can have a Lagrangian formulation of Maxwell's equations and the two are equivalent.
Андраш и Бычков, давайте мы прекратим эту сейчас дискуссию.
Это мы спрашиваем, я спросил.
2,5 часа заседаем. Друзья, давайте вопросы, потому что он как-то ответил на вопрос Бычкова. Теперь давайте попробуем высказаться, но у меня просьба, ну как-то сжато, не растекаясь мыслью по древу, потому что попробуем в течение 5 минут, не более, каждый выскажется. Вот я вижу, Климов поднял руку. Пожалуйста, Анатолий.
Андраш, я попробую по-русски, но я думаю, ты меня поймешь. Значит, ну, твой подход, и не твой, а твоих коллег, это я давно слежу за вами, он интересный подход, так сказать, особенно вот использование вот этого, вот, так сказать, вращающегося электрона, значит, с челами, когда вы там делали. Он впечатляет, и я думаю, он имеет какое-то будущее. Значит, единственное, что мне, значит, вот хотелось бы тебе посоветовать, значит, все-таки, значит, вот там, конечно, ты определять можешь все, что угодно, как угодно. Но вот когда ты вводишь связь между пространственной координатой и производной, так сказать, по времени и производной по пространству, значит, через c, то есть вот dx равняется c на dt. Ну, да. Это уже ты сразу жестко ограничиваешь всю вот эту алгебру свою, так сказать, которая позволяет больше, намного больше, так сказать, вам шагнуть вперед. Это вот первое. Значит, второе, ну вот посмотри, там у тебя есть разложение скорости света на две компоненты, так сказать. Ну, если вы уже заложили, что... вот это вот правильно. Значит, если же вы уже заложили, что у вас есть скорость света, так сказать, ну, это аналог скорости звука, так сказать, то вы ее, значит, вот, ну, как бы ты ее не раскладывал, так сказать, вот на две компоненты, значит, звук есть и свет есть свет. Он во все стороны будет распространяться, так сказать, ну, да, по принципу Гюгенса-Френеля со скоростью света. Его на две компоненты, так сказать, ну, мне кажется, здесь надо как-то вот это поаккуратнее сделать, так сказать, вот здесь какие-то, ну, ляпы явно, так сказать, просматривать. Тем более вы не рассмотрели случай, ну, а если будет навстречу или там поперек этого электрона дуть вот эфир, ветер, значит, ну и что тогда? Какой доплер получится, если будет вот навстречу этому вот образованию, так сказать, или вдоль него дуть ветер, поток эфира. Поэтому, значит, наиболее интересно, мне кажется, то, что ты, значит, вот вышел на нейтрино, и действительно над этим надо еще подумать, так сказать. Ну, наверное, это в письменной переписке, каждый сформулирует свои вопросы, она затронула больше всех, наверное, интерес у присутствующих, потому что, ну, значит, идея свежая, хорошая, мне кажется, так сказать, ее надо пообсуждать поподробнее.
Спасибо, Анатолий.
Спасибо за комментарий. И, конечно, это очень большой вопрос, что все это всегда постоянное или не постоянное. Это, конечно, большой открытый вопрос.
Андраш, ты еще ответил, я тебе дам слово. Владимир Львович хочет сказать что-то.
Я хочу сказать следующее, что, как бы сказать, извините, что по-русски буду говорить, что у вас не самосогласованная постановка. Вы пытаетесь получить данные об нейтрино и не знаете, что из чего у вас состоит ваша вся эта среда. Вы никаких вопросов, никаких ограничений на существование физического вакуума не ставите, не рассматриваете, как в нем распространяется электромагнитная волна в физическом вакууме. У вас вопросов даже этого не стоит. Вы привязываетесь к прошлому веку, к формулам Эйнштейна, и не понимаете, что в ваших условиях может быть скорость света больше, чем скорости могут быть больше, чем скорости света. И это никто вас не ограничивает, потому что у вас уравнение Максвелла.
Ну да, это я понимаю, что это тот же самый коммент, то, что Климов задал, и это, конечно, можно более продумать дальше эту теорию, и можно продумать, что будет, если все не постоянные.
Все не постоянно, тогда возникает вопрос, что вы понимаете под диэлектрической проницаемостью для вашей среды. Это принципиально, если вы разделяете скорость света и диэлектрическую проницаемость. Далее, у вас сразу возникает вопрос, что за волны у вас двигаются в физическом вакууме? Что они такое? Что они переносят? Почему вы имеете право пользоваться уравнениями, если вы их пишете не
для меня это более философический вопрос, потому что меня более интересует то, что можно понять в смысле экспериментов. То, что можно
на самом деле, извините, когда вы говорите, в эксперименте есть e квадрат плюс h квадрат, то она нигде в эксперименте не проверялась в целом. Она проверялась через только вектор Умова-Пойнтига. У вас половина вещей, они не проверены в эксперименте. Так что я понимаю, что вам очень хочется получить современный результат, но вы абсолютно забываете не субстрат, а основание, на чем вы это строите. У вас она получается тогда эклектическая очень задача. Вот здесь я использую уравнение Эйнштейна, здесь я использую уравнение, грубо говоря, Шрёдингера, здесь я использую соотношение де Бройля. А как они следуют из вообще своей среды?
Это немного по-другому, потому что наш принцип, что мы не используем эти уравнения, наш принцип, что мы используем уравнения Максвелла и уравнения релятивизма, general relativity. And we derive everything from general relativity and Maxwell equation. So we are not using other type of ideas.
А общая теория относительности, она же имеет здесь дело? Имеет здесь, если вы исходите из уравнений Максвелла? Где там сидит релятивизм?
Андраш, you will have a floor to give an answer. Володь, продолжай или завершай.
Я хочу сказать, что для Андраша нужно посмотреть над формулировкой базисной. Может быть, и не нужно ему использовать соотношения релятивизма. Они ему совсем не нужны, они его ограничивают. Вот в чем дело.
Хороший совет. Окей, Бычков
я сказал,
толковым замечанием правильным. И, если позволите, я тоже несколько слов скажу, и будем завершать нашу суперинтересную. Кстати, у нас сегодня было почти 40 человек в сумме. Так вот, ну, я попробую коротко. Во-первых, мне очень понравилась алгебра Клиффорда. Ну, она, кстати, она такая вот, один из видов только алгебр, который тут используется многими людьми уже многие годы. Вот. И я все-таки познакомлюсь поближе с этим, поэтому, если можно, Андраш, пришли мне, пожалуйста, свою книгу, я тебе деньги готов выслать за нее. Но я хочу, но, нет, without any joke, I can pay. Но некое все-таки негативные соображения тоже выскажу, критические, можно сказать, так? Дело в том, что... нет, вот то, что еще понравилось. Вот он распространил действие своей теории на все масштабы. Вот это тоже очень важная позиция в его подходе, в их подходе. Но мне кажется, вот на размерах уже внутри электрона, где ты полагаешь, что электромагнитного поля нет, вот этот подход уже не работает. И я даже знаю почему. Потому что на самом деле вот этот вакуум у тебя пустой, а вот если бы ты его заполнил, как вот тебя Климов призывает, да и Бычков, по сути дела, к этому призывает, заполнил этот вакуум чем-то, пусть для начала я его называю, вот этот начальный вакуум, я его называю реликтовый вакуум, то ты бы тогда там получил, что и скорость света у тебя там менялась бы, то, что вот Бычков получает, и многие другие чудеса, и в том числе поле не нулевое внутри электрона. Но вот по твоей модели, если вернуться вот к тому фрейму, который ты имеешь, мне кажется очень существенным, что ты почему-то не используешь запаздывающие потенциалы. Хотя это очевидная вещь. Вот этот самый Фейнман, вот аналогичные расчеты по электрону, то, что и ты на орбитале, хотя, кстати, не орбитали, а орбиты, мы в русском языке различаем. Орбитали – это квантовая такая физика, а орбиты, о которых ты говоришь, это физика классическая. Так вот, Фейнман в классической, собственно, подходе, по аналогичному твою, использует Ленара Вихерта. А ты об этом знаешь, естественно, я же вижу, но почему-то не используешь. Но в целом работа очень симпатичная, очень мне нравится, и это, безусловно, некий шажок вперед. Я согласен, Климов, по-моему, об этом говорил, особенно, что ты подтянул то, что нейтрино – это изоспин, это теория изоспина. Вот это очень здорово. Друзья, я думаю, что замечаний больше нет, хотя у нас тут несколько очень грамотных людей присутствуют, в том числе, вот, например, Булыженков, он там где-то помалкивает, ни вопросов, ничего не задавал. Вот. Ну, в основном все вроде бы так вот высказались. Поэтому позвольте мне на этом завершить очень удачное настоящее физическое обсуждение на нашем вебинаре. В следующий раз мы встретимся через неделю. Будет выступать Чижов Владимир с очень интересным докладом по работе никель-водородного реактора при комнатной температуре. Не при 1000 градусах, а при комнатной температуре. Посмотрим, как он это докажет и как он это экспериментально исследует. На этом заканчиваем сегодняшний семинар. Спасибо всем за участие. Спасибо.
Спасибо. До свидания.
Спасибо.